Okay, welcome. We're here in the Catalyst building. That's on the northeast side of the TUE campus, and we're here with the section Mechanics of Materials, where we have the lab, the multi-scale lab. So I'll tell you, come on in. I'll show you the multi-scale lab and what we do here. So here are some examples of materials that we're testing. So for instance, we're testing steels together with Tata, and you can see these crash boxes, and then there can be unexpected failure that occurs here. So we're really looking in detail on the microstructure of these materials and how we can understand the damage and failure behavior. Now, the purpose is to make the steel stronger, and Tata is actually quite good in doing this. So the cars are getting stronger, they're more safe, and the consequence is that you get these kind of scissors from the fire brigade, and they now start failing. And you can see here that there's an unexpected fracture occurring, and this kind of fracture also try to understand. Related again. Well, if you look at this kind of steel, it's corroded. You can see the rust on it. That's why typically you get a zinc coating on this, but the zinc coating can fail. And so this is zinc coated steel, and we're testing actually these coatings. These are actually very thin coatings, about 20 micrometer thick, and we're looking really in detail on the mechanics of these kind of coatings. Another kind of topic is turbine blades, for instance. So this is a turbine blade from an F-16, a fighter jet. But here, for instance, we were looking at thermomechanical fatigue of these turbine blades, and this is made of a super alloy, a nickel-based super alloy, and so the microstructure is actually very particular, and they're being subjected to a very harsh kind of loading, and we're studying this here. You really see the degradation of these turbine blades. Now, all of it, what I've said so far, has to do with steels, basically, or metals, but we basically look at all kinds of materials. For instance, we do a lot of research together with Philips, where we look at microelectronics, very thin layers, multi-layer stacks of different layers that are typically less than a micrometer thick, and we're trying to measure the mechanical behavior of these materials. Now, here we have some examples that look quite different. For instance, this is paper, where we can see cockling and fluting. That's basically the bubbling that occurs in these kind of papers when you have printing processes. So we're doing this kind of research together with Canon, where we look at the hygromechanics and hydromechanics of these kind of papers. Also with the Nederlandse Bank, the Dutch bank, we're looking at the mechanics of banknotes, and typically a lot of money is being wasted because these banknotes need to be taken out of commission when failure takes place. And we're really looking at mechanics at the fiber level, what's actually occurring there, and how we can understand this kind of failure of these materials. Other example is these kind of stands. The stand is being placed into your artery to keep your artery open, and this is sort of like a self-employment mechanism. So initially it's really very narrow, and it self-employs, and that the reason is because this material is a shape memory alloy. It remembers its larger shape, so it sort of like expands, and this kind of shape memory alloy we're also studying at the smaller scale. Now, we have a funky application here where we look at these breast implants, and particularly looking at delamination. You can see here that sometimes delamination occurs. Hopefully you can see this, and I'm trying to prevent this. Another application is historic materials. So we're looking here at historic paper. This is hundreds of years old. We're also looking at historic canvas. Actually, we are now testing canvas fibers from the Night Watch of Rembrandt from the Rijksmuseum. And we're also looking at historic oak. Maybe you can show it here already. There's a little sample inside. This machine is a micro CT scanner, and this little sample of historic oak is 700 years old, and we're looking at this, and here you can see, for instance, the internal structure of this oak wood. Yeah, that's then 700 years old. So this is all kind of, hopefully you understand that we're looking at all kind of classes of materials, and particularly we're trying to understand the degradation mechanism. There's often plasticity, damage, fracture, but also degradation due to influence of humidity, temperature, but also age over time. So all of these processes we're studying here. Okay, so how do we do this? Well, we're mostly interested in the mechanics, so we have all these mechanical deformation mechanisms. So here we have a device that's basically a punch test where we get these kind of specimens, and you can see that we can punch it and you get a fracture in there. And this kind of test is called a Messiniak test we can do in our microscopes, and I'll come to that later. Or we have a device here where we can do a bending. We can take microelectronics, flexible electronics for instance, and do a bending on this. Here we have a device where this device we can place into our micro CT scanner and do a test while we're taking computed tomography images. So in 3D we can see how the material is deforming, and some other devices that we developed here. So this is how we can do mechanical deformation, but we also want to see at the smaller scale what's going on. I already mentioned here the micro CT scanner that where we can see in 3D and we can do testing. But if we look on this side, we see all these microscopes. These are electron microscopes, scanning electron microscopes, where we can see in detail what's going on while we do a test. So come on, here I can show an example where we have here this scanning electron microscope, and inside, if you now open, we can see here there's a nano tensile tester that is actually too small to see, but really at this location there's going to be these very tiny little samples that are a factor of 100 smaller than human hair, and where we can actually do very detailed testing. So we can take the smallest samples that you can imagine, that we deform, we put a load on it, and then with a scanning electron microscope we can see at incredible resolutions, we can see how this deformation takes place. And I guess that's all like the overall overarching idea here. We always are interested in the deformation and the mechanics of materials and all kind of material systems, but we really try to understand it at the very smaller scales. And that's why we have all of these microscopes here. This is just one room of our lab. We have another room where we have a whole range of optical microscopes, optical profilometers, atomic force microscopy, scanning tunneling microscopy, nano indentation, all these kind of techniques to study the mechanics at the smaller scale. And we're open to study any kind of material, I would say, as long as there's a real nice, interesting question in terms of the mechanics and the degradation process. So that gives you a bit of an overview of what we're doing in the lab, and I would say that the sort of like broadness that we have in terms of the materials and material systems that we're testing. Thank you.